And when linear regression is not able to solve our problem, there is a likelihood of using logistic regression. Logistic regression is the regression that uses the type of regression that uses simply linear regression in itself. For example, this is the scenario when linear regression, which means creating a line that would fit the pattern of the points distribution or the data distribution, is not going to fit, and there are ambiguous areas, then zone, we try the next type of regression, which is logistic regression. And logistic regression, or the sigmoid or logit function, was a function that we said could fit. And then just obviously this graph, the graph that you see with a pink line, is the graph that gets represented by this formula or this function. And this function is logit or sigmoid function, which we call it logistic regression. And logistic regression, especially the exponent of E, gets replaced by a linear regression. As you can see, formal features like x beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. This x, which you see minus x in the formula, is represented with a linear regression. And so we call this logistic regression. Logistic regression. And it basically gives you the probability of an just a value to assume one of the possible values. And we discussed about this. So we call it a logistic regression, and we basically define a threshold value. And based on that threshold value, the value could be either a success or a failure. And the graph goes like this. And here, so this is among the probabilistic models, the logistic regression, as an example of a probabilistic model. And there are non-probabilistic models that enable us to classify values. And among them is a support vector machine or other probabilistic classifiers, such as knife bias classifiers could be used for classification purpose, depending upon the number of classes that you have. And the performance of classification model can be evaluated using confusion matrix. And we discussed about confusion matrix and different metrics of classification. One of which is a confusion matrix, where you can have like just the number of correctly classified values to the class, a number of the number of items that are the number of data sets or data points that are not classified or predicted to the proper value, and this you have such a classification, a confusion matrix. A confusion matrix enables you to calculate the performance. As you can see, just in this graph, we said we can have predicted value as negative and positive, but actual value as negative and positive. Then just negative to negative, it is called true negative. Positive to positive, it is called true positive. But when you expect the actual to be negative, but the predicted value is positive, you call it false positive. When you expect when the actual value to be positive, but the predicted value is negative, you call it false negative. False negative, false negative from the perspective of the predicted value. And true positive and true negative are the actual targets that you see. And some algorithms flip like the actual on the top and the predicted on horizontal. The actual could to be represented vertically and predicted to be horizontally. So just this actual and predicted can possibly swap. Predicted could be right here on the actual. The actual could be right on the predicted location. So just the table could potentially rotate. In any case, the point is you can measure the performance of your algorithm, your model, by using confusion matrix. And it's not only just for binary classification, but also for multiple class or multi-class classification. If you have more than 2 classes that you want to train a model and just predict the corresponding values, then you can have multiple classes horizontally and then just multiple classes as predicted horizontally, the same number of classes vertically as actuals, and then just you can evaluate the confusion matrix. So this is one way of evaluating your classification model. And there are other classification matrices, accuracy, and accuracy actually gets calculated based on this confusion matrix, like using these values: true negative, false negative, true positive, no, false positive, true positive. Using these 4 values, you can calculate different matrices, like such as accuracy, or the true positive rate, or the true negative rate, or precision. So these are the values that you could calculate. And just based on graphical representation, precision, sensitivity, specificity can also be calculated just using this graph, and ensure that you're going through these details. And ROC curve, we finally covered the receiver's operating characteristics, and what the area under the curve or the ROC curve mean. The larger the area, the better, like just the higher the performance of the model. And that was larger the larger the area, the better the performance of the model. And if you can evaluate multiple models using ROC curve, and like if you have an ROC curve which is at the highest position, that means the model that's represented by that particular curve performs better than the other models. So we discussed about that. So today we will continue discussing about one additional supervised machine learning model, which is classification with decision trees. Classification using decision trees is the easiest classification, because if you remember from our data processing steps, some algorithms would require our data to be normalized, our data to be transformed, and these algorithms would need some additional data processing steps. But classification with decision trees don't necessarily need any transformation. You can have the data as is, and then use if else conditions to classify, to train a model. And then just using a data, you can train a model by simply using just the raw data, by simply using if else conditions. If you go one direction, if the condition that you want to be satisfied doesn't get satisfied, then you go to the other direction. So just you basically split your data based on a condition to the right or to the left, and ultimately you create a decision tree. So this is what it is. CART is an acronym which means classification and regression trees. It can be used for both classification and regression, and classes of models that use a tree-like structure to divide the data. So classification and regression trees are classes of models that basically use tree-like structures. And the algorithms are built on a series of conditional statements, which is if, else. If a condition gets satisfied, you go one direction, else you go to the other direction of the tree. So the tree always gets divided into two directions. One that satisfies the condition, the other that doesn't satisfy the condition. There is no in between. And the advantage of classification and regression trees are simple to understand and interpret, because you can easily explain to anyone about the model, how the model treated the given data, because you know the conditions or the rules that get generated as a result of the training process. And there is less data pre-processing required, because you don't need to scale or transform the data. You can simply use the data as is without any transformation or scaling. Which eliminates the need for data pre-processing. And since there is no need for data pre-processing, and it always divides the data, your data to just in a tree structure, the computational cost of training classification and regression trees is very small, and just they are computationally quick. And the disadvantage is potential. So since they are very simple, they can easily overfit. And also can generate a completely different tree with a slightly different data set, because since it's conditional, and then basically just it cuts at a given point. The moment like the center of the conditional value moves a little bit, then the tree will, the final tree that gets generated will be completely different for a smaller or a slightly different data set. So it just is prone to slight change in the data set. So those are the disadvantages. For example, a model or a flowchart involves a series of questions and narrow the possibilities. The tree only splits and never merges. Basically, just it always splits. For example, if we are creating a model for a restaurant to predict the number of customers, then we can have different attributes. And let's say just or values. If the model, if we take the data, and is it weekend? Yes or no. If it is yes, then just we go to one direction. We go to the right direction. If it is no, to the left direction. If it is weekend, then just it is yes. Is it near major or yes or no? Then we move to one other direction. If it is yes, we might predict as could be 1,000, or the other to 500. Or if it is not weekend, then is it after 9 p.m.? We like on a weekday. Is it after 9 p.m.? Then if it is yes, we go about 400, or no, we go about 100. So this is how we basically just classify. You can read more about classification trees, but the general gist of it is classifying your data into binary directions, with a yes or no, or like if a condition satisfies to one of the direction, if the condition, the given condition that you're checking with the data at a point is to that doesn't get satisfied, you go to the opposite direction. So that's how you basically create such a tree. At the bottom, it's sufficiently narrow. It provides you a sufficiently narrow situation, and then just you either label the final leaf or set a value, and then just you can get a prediction value at the end at the leaf level. And the other approach is there is a concept of ensemble learning. Ensemble learning is something that most commonly used, and most of the time when you want to have a model that learns more about the entire data set, you might train multiple models, model A, model B, model C. So, and then finally, you could train multiple models, and each of these models get trained on a subset of the data, and then all of these models vote finally on a new data. You basically let these models to vote about the fate of that new data, and finally a voting can happen, and as the end you set the corresponding output of that particular data. So this scenario is called ensembling. Ensemble learning is using class of algorithms that leverage a large number of similar predictors, and you could basically like just use different algorithms for model A, algorithm A, for model B, algorithm B, for model C, algorithm C, but the same data can go through each of these models, the same data, each of these algorithms, and then you train three different models from three different algorithms of the same data set, and finally each of these models could predict their corresponding value based on their learning to that particular data, and then just they will finally vote on the output of the data on a given data. So this kind of learning is called ensemble learning. If you are training multiple algorithms to generate multiple models, which would collaborate at the end. Collaboration is best. It's not about only a teamwork at workplace to produce some useful output or like just efficient to an increased efficiency or a great performance to have a great performance, but also in machine learning, a teamwork of a team of models can work together and generate an output. This is called ensemble learning. And the common types of ensembles, especially in relation to the classification trees, without just losing our focus on the classification tree that we just started, bagging or bootstrap aggregating. Bagging means B is for bootstrap, aging means for aggregating, bootstrap aggregating, and then each submodel gets a random subset of the original data. This is in the case of classification trees. So in case of classification tree, given a training data, then you basically given a training data, you basically train classify the data set into subsets. Each of these subsets will be used to train a certain classification tree. Like just for example, model A is one classification tree, model B is another classification tree, model C is another classification tree. So these three models are three classification trees, which are trained on three different subsets of the superset, the super training set. Then finally, you have these three models trained on the entire data set, but each of them don't overlap in the data set that they used to be trained and get generated. So finally, you will have these different models, and then just you will use for a given data set, you will use one all the three, and then just you choose which one is the best performing. And each submodel gets a random subset of the original data, and then they will be stacked, and the output from each subset is feed forward into another model. So there is that potential as well. And now this is an important thing, that to see the forest through the trees. To see, it's better to see the forest through the trees. And bagged trees or bootstrap aggregated trees, each tree gets a random subset of the training data, and then with replacements, some data points can repeat multiple times. And then the random forest regressor or classifier is one of the, it uses like the bootstrap aggregating approach, but more. In addition to bagging, random forest also applies features for each tree are also random subsets. So it is important to note here that bootstrap aggregation uses different subset of the data. Let's say we have a data set. And then just we want to divide the data into three. So this is data set A, data set B, and data set C. So this is the entire data, data D, right? The subset of A, subset B, subset C, and this will create model A, and this will create model B, and this will create model C. So this is bagging, okay? Bagging, which means bootstrap aggregating. Bootstrap aggregation relies on randomly generated subsets of the entire dataset. Bagging is gets created like this, but random forest regressor uses bagging. This uses bagging plus feature selection or random features. In case of bagging, we subdivide the data just the way we did it. This is bagging. But in case of random forest regression or classification, we also randomly select subsets. So the features of the feature set, if we have, let's say, this data set has 10 subsets, 10 features, all the 10 features are not going to be just in case of bagging, we use all the 10 features. But in case of random forest regression, we don't use all the 10 features. Instead, at time for model A, let's say we might use 8 of the features. For model B, we might use 9 of the features. For model C, we might use all 10 of the features, right? So this is what random forest regressor would do. But like classify just subdivide the data set and also randomly select the features. And at times you could use all the features. At times you could drop some of the features. So this is what random forest regressor or classifier means: bagging plus randomly selecting features or using random subsets of features, which means not either using all of the features or using some of the features, depending upon the randomly generated subsets of the features. So again, bagging means ensembling. Okay, you would be generating multiple models. If you are generating multiple models, which contribute to the overall prediction of the tree, having multiple trees, then you are using ensembling techniques. So in this case, what was going to happen is each tree that or each model that you generate is going to be completely different from each other, right? And they contribute each of, and plus they will use, given just a new data, they will basically get applied differently and could just generate different output, and from those different outputs, then just we get a voting mechanism, and finally you pick the most voted value of the prediction. The most voted value of all the models would be the value of that particular like the value for the new data set. So every tree is built a little differently, as we saw. So different subsets of data in case of bagging or bootstrapping aggregation. Again, in the case of features, we said different subsets of the features are available at each split. Then this entirely is the random forest regressor. The random forest regressor does two things. The first is just using the subset of the data, and the second is using the subset of the features in each scenario. And we could have like multiple models for a given data set, because as long as we can have the data subdivided however many times, so we can have this model A, model B, model C, model D, model E, F, G, and model H, right? We have like these 8 models generated, 8 models, right? Each model is randomly, they are not equally divided, they are random subsets. So the data is random subset, and also in each subset, the features are also random subsets of the full features. And finally, you have this combination. So so increased diversity of estimation, basically just you diversify the data. Basically, this is to minimize the overfitting. If we simply just use tree-based classifiers, just the vanilla tree-based classifiers in one run, then we make the model prone to a minor data change. To avoid that, we basically split the data into multiple data sets. Furthermore, to again avoid overfitting, since overfitting is directly related with the number of features that can potentially be used in a data set or improperly used in a given data set, then we basically just also take subsets of the features that enable us to minimize the overfitting in 2 counts. One, you take subset. Second, you subset of the data set. Second, you take subset of the features. So that basically makes it our data minimize overfitting. So then So increased diversity of estimators or models, we have instead of just generating one model, we have 8 models that vote. So each of these models vote to the final model, right? Each of these model vote to the final output of the model. So 8 voters will be there, and then finally this is considered as an output of a single model, but internally there were 8 models, and in reality the number of models will be in thousands, especially just in regressor, random regressor. In any case, some concepts increase diversity of estimators or models, and same concept as obtaining large sample size, and then for statistical reasons, large uncontrolled data points, uncorrelated data points, it's important. We have to at least just ensure that the attributes that are involved or the features that are involved are not correlated to each other. We have to avoid at least the correlation, and it basically gives much more information. If they are uncorrelated, means if you remove the multicollinear features, if they exist, you have to remove one of them from the pairs, and then just ensure that they are not correlated. In that case, you get much more information. And large ensemble of trees protect against one tree misbehaving or overfitting. This is the important point, which is you basically avoid overfitting, because the large ensemble trees, the number of you have, instead of dealing with one model, you have 8 models in this particular scenario, plus in each of these models, the number of features could be different, because we randomly select features for each of the models. If we have, let's say, 15 features, some of them could be maybe between 8 to 15. This is an example. Some models could use 8 of the 15 different, and the others could be a different 8, 9, 10, up to 15. Maximum of 15 features can randomly be used in 8 of these models, and then this basically avoids overfitting. And the advantage, as we touched earlier, ensemble methods or using multiple models trained from a single data set protects against overfitting. And each tree is built on a different slice of the data, and even powerful or deep trees can only fit to some random subset of the data, and only some of the features are available at each split. So this is basically just why we do, and as a result of this, we avoid overfitting or reduce overfitting. And in general, adding a small amount of randomness is a key. Small amount of randomness is a key component of many algorithms, and artificially create statistics forces algorithms to interpolate or extrapolate beyond given data points, which means you can interpolate or extrapolate. You can generalize from a given data set, because you are creating artificial environment where the data could be different, because you are training multiple models using a given data set, just one data set. So you can have multiple models, and each of these models create a scenario where you can have a scenario where you can have multiple models trained on a smaller subsets of the data, and then that gives you enough opportunity to deal with deal with the potential overfitting scenario that could happen because of your data point. And then those some of the edge cases would be handled by one or more of the ensemble models. And it can get probability scores, ratios of trees that voted for a certain class or probability of that class, and then not a true probability, but often used as a stand-in, and basically gives you a random right amount of generalization. For example, if you see a simple decisions tree, you can see how complicated the graph is. In this scenario, it's like just a graph so complicated, and we're trying to create like just fit following each of the blue line, and then just this could highly likely be messed up with a slight data point change. So this is not reliable. Instead, we can use decision tree with bagging. In that case, we will have somehow a smooth line break whereby we can live with leaving some of the points outside from the class that we wanna we want them to be, and most of the classes covered with the classification, the decision boundary. So this decision boundary is the right decision boundary. Any data that would potentially come on the green side would be classified as the same as the blues, or any of those that come on the orange side would be classified as, on the lemon side, would be classified like the lemon. But there are some points, so we would leave with them just. So this is the right amount of generalization. Right amount of generalization means just deal with some incorrectness, give some room to not to be correct. In otherwise, if you want everything to be correct, then just you will have such a weird line that tries to have everything under control, which is impossible in a real machine learning data set trained model. And the disadvantage of this multi-class based or random forest regressor, random forest regressor, RFR. Remember, we said this is bagging plus random features, right? So, and these could result in multiple models. Multiple models. And so what are the disadvantages? Now, loss of interpretability. When we started the classification trees, because they are based on if-else conditions, given a data point, it could be either this way or this way, a yes or no. Now, this is for one tree. In case of random forest regressor or bagging that also involves random randomly selected features, we will have, instead of this, we will have n models or n trees. And those n trees are not controlled. We don't know these trees. Mainly just the algorithms create these, and it becomes very difficult to interpret. In case of one tree, it's okay because we know the effects. In case of n trees, it's very difficult. So what are those cases? Loss of interpretability. Unlike a single tree, it's impossible to visualize or understand how hundreds, in reality, or thousands of trees make a decision. As a result, the probability scores do not actually reflect probability. As a result, you won't be able to interpret, so you will lose interpretability. In the case of 1 tree, you have the if else, and you know just how to interpret the data. In case of n trees, it's very difficult, it's very complicated. And large file size, because since you are generating multiple trees in the overall training process, you will potentially have a model that would be a large file size as a result of the training process. And models need to store all the trees, all the multiple trees in the forest. So now this is about the supervised machine learning process. And I see a hand raised, Tariqa. Do you have a question? Please type on the chat. If Tariqa, if you have a question, you can write your question, or I can let you speak. Tariqa Tasfa. Do you have any question? So remember, we covered 3 supervised machine learning models. Simple, linear regression, right? Simple linear regression, logistic regression, and classification trees. Classification tree, the single tree, the bagged tree, bagged or bootstrap, aggregated, and the random forest regressor or classifier, which is bagged plus random forest, random feature. So we just covered, the simple linear regression and also multivariate linear regression were touched, variate linear regression were touched, and logistic regression, logit, and the classification tree, which is a single or bagged or the combination of bagged and random. So these are the all supervised. Supervised, sorry. Supervised machine learning, ML algorithms, okay? Supervised. The reason why we call them supervised is in simple linear regression, we target a value. We have labels, so they have labels. In case of linear regression, we also have label to decide. In case of classification, we also have classes, a binary value, true, false, kind of classes, or we could potentially predict values, continuous values, depending upon probabilistic voting. So random forest regression, the random forest regression can be used as a classifier and also as a continuous data predictor. So these all are supervised machine learning models. Any questions around here? Otherwise, I'll be moving on. In the sampling technique, could those subsets of data set be overlapped or completely distinct subsets? Very good question. So they are completely different data sets. And then just in case of ensembling, especially, we want the data set to be completely different. We don't want to train one with another data. The reason is we want them to learn a different portion of the data. But when we use, let's say, just we have random forest regressor. A random forest regressor can have 100, let's say the smallest, 100 trees. Okay, when we have data, we don't know new data. New data, we basically feed this new data to all the 100, and each of these 100 trees could treat the data as individual, and 100 of just the data will go through the hundreds, and at the end, all of them will vote at the end, right? So each of the trees during the training process should rely on a subset of the data, a subset of the data without overlapping. At times, some portion of the data could potentially be repeated, but not this internal implementation depends on how the algorithm is written. In most cases, the subsets don't overlap. How do we validate random forest? Very good question. The validation of random forest regressor is evaluated based on root, mean, square, error, right? Root, mean, square, error. So basically, this is like just the square root of the predicted minus the actual, all values, the square, divided by the sum of this, divided by n. So this is how you would calculate the performance. This is RMSE. So you would calculate root mean square error, the root mean square error of the predicted minus the actual of each value. The model gets calculated. The performance of the model gets evaluated, and this is the sum. The reason why we use sum is because we are evaluating the performance of the model using the 20% or 25% or 30% of the data set that we use, because this is since this is more than one, could be 10 or thousands. For all the thousands, we calculate the difference between the predicted and the actual and square it, divide over n. So what are the major criteria, and we should base on when we classify subset of the random forest or given data set, or are they always given by default? So you don't do that. So the algorithm, the random forest algorithm, does that for the algorithm does that for you. The subset is just hidden internal, the implementation. Unless you are in the business of implementing a random forest algorithm, you don't basically just get into the details of dividing the data into multiple subsets, right? Instead, it basically gets divided for you. It gets divided for you. The algorithm takes care of randomly. So this is for you to know what to do, and how we can penalize or smooth overfitted values on linear regression. So linear regression is a different thing, but if we are talking about random forest regressor, basically just you would be using random RMSE, and there is a concept called hyperparameter tuning. So you would have to, random forest regressor has other parameters that you would have to, just the algorithm will have, has values that you would basically twin. And those twinning involve, I think at the end of the code that I was showing you a couple of classes ago, at the end, there is grid search, right? Which is a hyperparameter twinning of the algorithm. You basically just fine tune the algorithm to get the least, the smallest to minimize this RMSE. So you would have to twin the parameters of the algorithm to basically, that's how you would get the best model. Any other question? Okay, moving on. Now, so in case of unsupervised learning, we will be discussing about unsupervised machine learning algorithms. The first one of which is association rule. At times, we wanna get association between data points. To begin with, just to to help you recall what supervised and unsupervised machine learning model means or learning means, here is just a single slide where you can see. In case of supervised learning, the type of learning that we covered last, right? In case of supervised learning, which this involves, right? This involves, this involves the simple linear regression, multivariate linear regression, logistic regression, logit, and classification trees, right? This is what it is, supervised machine learning. So simple linear regression, multivariate linear regression, logit, classification trees, or random forest, like just in classification trees has multiple of it. The single tree, the bagged, or the random forest regressor or classifier. All these are supervised. Why? Just how? Why we call them supervised? Because all of them have target or label which is included in the training data, and the models learn to predict, and they are guided by the target or the labels in the training data. So this is why we call supervised. The supervision is because the value that the model is to predict is already associated with the data. The model will be learning from the data itself to predict what value it is expected to predict. So in the process, we basically get the best confusion matrix, the matrix, right? Matrix. It could be confusion matrix, or it could be RMSE, right? Depending upon the type of model. Root mean square error, or a best confusion matrix, or accuracy in this case, accuracy or precision. But in case of this, root mean square error. So we have supervised models that we deal with labeled data or target data that are already included within the data set, within the training data set. On the other hand, unsupervised learning are learning without any label or any target value included. And some or most data don't come with any target or labels. In this scenario, you'd have to use supervised, unsupervised learning. And some problems do not require prediction, right? A prediction, you don't have to predict, or no need for target label. The data itself contains some internal structures that help identify different data points. This is what is important, which means some internal structure. What that means is a pattern. Okay, a pattern, natural pattern, natural pattern. Naturally, for example, when you like just in a smooth scenario, naturally, like just imagine your behavior, your personal behavior. You personally do things, and then just in a predictable manner. Monday morning, if you are a student, you go to school, and just your classes are known. You attend classes, and then just at the end of the day, you may go to library, and just that's how your Monday looks like. And Tuesday, you may have a certain pattern. Wednesday, Thursday, Friday, throughout the week, you may have a certain pattern. So that's how you operate. And some other person operate in a different way. But just collectively, if we study students of computer science, they may focus on similar kind of pattern. But for an external observer, we don't let any detail, but we simply collect the data that what you do. From the data that or what you do without telling the external observer, a machine learning model can identify pattern of your day-to-day activity, right? Your day-to-day activity. That's one thing. And another thing is, imagine about your mobile phone. You use your mobile phone in a certain pattern at a certain day. Maybe like just you turn on your data, you use it at a certain time. You may call someone on the other end. You may use your VPN, or you may use WhatsApp or Telegram or Facebook. All that pattern can be tracked from your mobile. And we are not talking about a single you. We are talking about all of you all together. And then just based on your data consumption, some pattern can be identified. But this pattern does not necessarily need to have a target or a label to the data. So this is how the unsupervised machine learning gets applied. So this kind of scenarios. Another example is your banking transaction. Different types of people on the market or different customers of the bank will have different patterns. And then just those kind of patterns can easily be learned by simply looking at the entire customers of the bank. And based looking at the entire customers of the bank, we could identify, oh, some of the customers just get some transactions maybe 3 times a day. 3 times a week. Sorry, 3 times a month. Just once. One transaction is when they salary gets deposited. Another transaction is when they withdraw some money, right? Another transaction is maybe like just on somewhere at the end of the month they get another withdrawal. So that's it. Three transactions per month. Or if the customers are like just merchants or traders, then just these people may have multiple transactions on their data. And based on that pattern, if people like you who get their salary paid and then just don't exceed maybe 10 transactions per month, if something gets found, which is 15 or 20 transactions per month, that means there is something wrong. So this is out of the pattern. So this is a kind of unsupervised machine learning. So so this is basically the difference between supervised and unsupervised machine learning. So what can we do without supervision? Then the common applications are, so just the scenario that I was explaining was clustering data into distinct groups. For example, market analysis, or in banking transaction analysis. A banking transaction analysis that I told you could potentially classify customers of a bank as the most frequently customers with more frequent transactions versus customers with less frequent transactions, or even within the most frequent transaction, customers who are doing a certain type of business. One cluster. Another cluster is a different type of transaction. So this is in the case of banking, or in a market analysis. Different customers may buy different products, and you can identify their interest area. You can infer based on their purchase what kind of people they are, what kind of spending they have, and things like that. So that gives you a certain pattern. For that, you don't necessarily need to know a certain target or a certain level of the data. The other application is associating different data points, or using recommender systems. And this is very common in the Western world, because you identify people by their custom, their behavior, their market behavior, and then you basically just provide more of those behaviors. Another recommender system, just the most common one, is if you are using TikTok or YouTube, the recommender system, you can see the recommender system. If you are inclined to listen Amharic news of a certain type, the YouTube will basically give you more of that type of news. If you are listening English, more of English, American-oriented news, or more local American-oriented news, that's a recommendation. Or just a global news, more oriented to, for example, just Russia versus Ukraine war related stuff. So the recommender system basically learns from your behavior and then just gives you more of what you need. So that's another application of unsupervised machine learning. And detecting anomalies, fraud detection. Just as I said earlier, based on the number of transactions that most customers do with a bank, then if the model notices and like just out of the usual pattern, basically it detects that kind of fraud. And dimensionality reduction is another approach. Dimensionality reduction means you may have like just thousands of features in your data set. And instead of just dealing with those thousands of features, some of which may not be applicable for a type of problem that you're dealing with, you can cut most of these dimensions into manageable set of dimensions that you can deal with. So that's dimensionality reduction. Then it can still be used for prediction as a clustering algorithm. Clustering can cluster data into multiple groups, and then just a new data can be based on the clustering algorithm, can be calculated to belong to one of the clusters that are created using the unsupervised machine learning. And it doesn't necessarily learn what the data points are. Instead, it learns the differences or similarities between the data points. And association rule, I suggest you read more about this association rule and the problem setup, continuous variables for ARM association rule, association rule mining. That's what ARM means, and related to continuous values, computational cost. So this is association rule is one of the rules, one of the algorithms that I suggest you reading through. And if you have any question on this, I want to cut the class short today for some personal reason. And so in case of association rule, there is a concept called pruning, because association rule involves some cost to deal with all possible rules that may get generated. Then just we apply a mechanism to cut some of the scenarios, some of the rules, so that we can have very limited number of, manageable number of rules at the end, or manageable and applicable number of rules that we can deal with. And pruning, I suggest you reading this the association rule part, and I will go to the a priori algorithm. So recommendation engine is based on association rule mining. I'm going to leave this for you to read as one of the unsupervised machine learning. And the most common unsupervised machine learning is clustering. Clustering has got two flavors. One is a k-means clustering, and the other is hierarchical clustering. We will basically just touch base this clustering technique. And clustering, we also saw the clustering technique in the end-to-end machine learning code. So I suggest you go through those. And clustering has got dividing and grouping the data and segmentation of the data, which involves the population of the data into several, dividing a population of data into several sub populations, and grouping similar data points together, and then so that the data that are grouped together are different from the data in the other groups, but more similar to the data within the group. And it can basically, like, just the approach gives you insight into the structure in the data, and also the distribution of the groups in the data. The application of clustering is customer segmentation. In customer segmentation, you can cluster, or you can subdivide your customer base into multiple classes, so that you can basically deal similar customers in a similar way. If you are providing discount for your customers, you don't provide discount for everybody, because let's say just you have a shop, you have a physical shop. Let's forget about the online marketing. In Ethiopia, if you have a physical shop, let's say for example, a big supermarket, like the one in around Megananya, Zafmesh, a supermarket under Zafmesh building, a big supermarket. And imagine that supermarket tracks its customers. So this kind of customer segmentation should also requires to know your customers, to have data about your customers and their purchase history. In US, you have a customer number wherever you go. Usually, like just in your neighborhood, there are shops that basically use your phone number like as a customer ID. Your phone number is unique to you, and that can be used as a customer ID. And that customer ID, whenever you purchase some item, you basically input your phone number. What you're doing is you are associating your purchase with that phone number. Every time you purchase set of items, you don't go to a shop to buy one item. You go to a shop to buy multiple items. Every time you purchase, you basically insert your phone number, and then your purchase gets associated. What that means is your purchase history is being tracked And based on the type of items that you are buying over uh, uh, just over a period of time, the shop knows your behavior. And obviously, a family usually consumes similar type of items. And since your shop knows your behavior, it basically just uses that shopping history along with all other customers. Then just it uses clustering to group you among other customers. So based on that data, it knows what is common among you and all the other customers, and not common with the other group of customers. Some of the customers may be like just a well-to-do customer group who buy a high-end items, any other customers a low-end items, and depending upon the type of customer you are or you are grouped with, you may be given a discount. Or you may be expected to pay a certain type of price. But although the price is labeled, but as soon as you input your phone number, since you are clustered with a certain group of customers, you are identified, and then just you basically be given some sort of messaging or discount or any kind of treatment that your customer group uh, uh, is eligible for. So the application is customer segmentation. Customer segmentation for targeted marketing campaign. The targeted marketing campaign could be selling a new product. A new product. If that new product is not applicable to the type of product that you are buying, they don't show you because they know where you belong to, and it only shows that new promotion to they only show that new promotion to the group of customers who are buying an item similar to that kind of item, or if they are doing some discount for a certain group of customers, and if you don't belong to that group which is targeted for a discount campaign, then you won't be given because you are already clustered as just as part of the group of customers who are not eligible. So, and the other is insurance, identifying high risk drivers or kind of land use, finding similar areas of land for particular use. So this is some of the applications of clustering. And partitioning algorithms are among the partitioning algorithms are the K-means algorithm and the support vector clustering, the support vector machine. K-means clustering divides the cluster into a given data set into multiple clusters. And these partition algorithms attempt to create meaningful partitions of the data by constructing different groupings. And they typically be done iteratively. And each iteration improves the groupings. And sometimes it involves predefining the total number of groups. Maybe like just you start with a certain, now this is group 1 and group 2, group 3, right? Group 3. And it's, you know, you may start with 3 groups and then just change. So K is, in this case, K is equal to 3. You may try K is equal to K to be 4. So on the same data set, you may try K is equal to 4 or K is equal to 5. But how just this is a value that you play with, K, just the value of K, trying to subdivide your data into multiple groups. And there is a way that you know what is the true value of K. This is called the elbow method. And the other type of clustering is hierarchical clustering. Hierarchical clustering is dividing your data in kind of hierarchy so that you either start with a smaller number or with the entire data as one cluster, and then just you continuously divide. And there are different techniques to measure similarity among the ones of measure similarity between data with to stay in the same group are the Euclidean distance metric, or another is a cosine distance metric, and the third one is the Jacquard distance metric. These three metrics are used to identify whether or not like just points are or data points are similar or not. So I suggest you reading through these values. There is an example with a 2D data set, and the distance metric is also given. I suggest, and the Euclidean versus cosine distance are given between 2 points. To point 1, you have like A, B, C, D, E, F, G, and between these points. So you can see the distance metric and what K-means clustering means. And I suggest I leave these details for your reading. And one thing that I would let you know is if you in an earlier slide, I said you play with K is equal to 3 or 4 or 5, and then just how do you know what is the correct value? Is that 3 or is that 4? Is that 5? The technique is called the elbow technique. The elbow technique. Each number, this is K. K is equal to 2, 3, 4, 5, up to 11. And so if you see this looks like an elbow, right? Right? This looks like an elbow. At this point, you have the elbow. So this is the elbow. Imagine this is like just a hand of some 10%. So these are the fingers, and this is the elbow point. So you see, so the elbow at the elbow point, you get this. What that means is the distance, the variability between, like this is the K measure score. These are variabilities. The variabilities are drastically changing, dropping, and then just at this point, and then the difference between here, from here to here, is very small, and then just it basically doesn't change anymore. What this means, if variability doesn't change anymore after a certain point, so the value that you have at that point is the correct number of clusters, which means we started with K is equal to 2 and went all the way to K is equal to 11, but K is equal to 5 is a correct number of clusters. So this technique is called elbow technique. So it's important to note what the correct value of K is. And the cluster in order, this is the hierarchical clustering. It's not just the most common type of clustering, but I suggest you reading through this. And there are different types of linkage between the centroid or between the points in different clusters. It could be a single linkage to measure between the differences, or we could be completely just the maximum distance from the farthest points of the groups. So this is one group and this is another group. This is one group, another group. In this case, the closest points are being measured. In this case, the farthest points are measured. The farthest point measured is a complete linkage. The closest are the single linkage, or the average linkage is for each point we calculate the distance between each point, and then we calculate the average linkage. Or we simply take the central point, the centroid of the two groups, and then calculate, and then just these linkages, the centroid linkage. So this is what I have for today. And theoretically, we have everything that you need from the supervised versus unsupervised machine learning models. And this is to help you go through the theoretical aspect of the foundational machine learning concepts. So today marks the end of the class. If you have any question, you can send me an email, and I expect the homework to be or the project to be submitted. And please take your utmost effort to do your best on the project, and we will be evaluating it, and then just make it a standard project for your own sake, and apply. As you know, the class that we covered over the last 9 weeks is not a complete one, but it kind of scratched the surface. I basically touched some of the concepts that you might need to understand, but I gave you detailed books that are used in about 400 universities in the world, right? One of the books that I shared with you is a book that is very popular in the world, that you can get the most out of it. And I may have to go back and open that as a closing from our email communication. Okay, just give me a moment. I am opening. Yeah, so here are the resources that I have been sharing. Okay, this only goes all the way to the 7th, but let me open the 8th. Yeah, so this includes up to all the way the last week. All the recordings are being shared in the past, and then the books that I was, and then just the resources that I have here, in the books that I shared you. This book, which is like the D2L interactive deep learning book, or dive into deep learning. This book is very popular. It's like just it's only 2 years old, and it's popular in 400 universities throughout the world. So you just make the best use of it when doing your project, and you could get example data sets that could align with your data set, with your project. And on the other hand, the Python Data Science Handbook is a free book that you have available for you, right? And I share the details in just example data sets, and the code, everything is here. And since all of you are instructors, like you know that just as we cannot cover everything in class, but we basically scratch the surface, and we let for our students to dig the details. So you are expected, as you expect those things from your students, you are expected to do the same for the sake of this project. So the project detail is here with the corresponding instruction. Most of you are or have already submitted your project proposal, and continue doing that. There is a reward, and I will be discussing on the submission date. I was composing an email. The next week is not going to be the end of the class. Instead, we will be extending because of the class, because of like the new expectation at universities. I know that just most of the universities right now are on graduation schedule, and also the ACLC examination and the exit exam at different universities. I want to discuss with the coordinators of each of the 6 universities, and then together we will decide when we will cut the final date. And also, I know at Jimma University and Gondar University, there are students who are taking this as a course requirement. I want to close on that. In the next 15 minutes, I will be discussing with the coordinators of the universities. And if coordinators, if you are here, please stay behind, and I will be stopping the recording, and we will be sending the final submission date. And FYI, I will be coming to Ethiopia, and if we can arrange the certificate offering and project completion date aligned with my presence in Ethiopia, that would be nice. So we will be discussing with the coordinators on the logistics and evaluation, the submission date, the evaluation, and also like just the project, the certificate offering on this program. Okay, any question? Any question? Reference book 2. Reference, which was the reference book? There is a question from. Okay, reference book 2 is which one? Python reference book 2. Okay, this is the reference book 2. Let me quickly check. Any other question while I'm opening this? Okay, so this is reference book 2. Reference book 2 is provided as is. There is no PDF of this book. The reason is this book is for sale, so they don't give. They won't give us the PDF. If they give the PDF of this book, nobody will buy it. So it is for sale, but the content is provided as is online, just in order and the corresponding. So I really love just the way this book is structured, and most of the things that we discussed are already here. So you can basically just go through the details. Most of the details, most of the contents, and all of the contents are in this book, but in a very detailed manner. And as a bigger reference to this one, the other book is also has some details, which is this one. This is the other book that I said is adopted at 400 universities from 60 countries, and then just make our universities part of this these 400 universities, and you can benefit from using it. And just this book is also a detailed book in many ways. So just do the research, and your participation in the project, in the final project, is important. It is important, and making your project to win, solving a real problem. I know we didn't go deep into the details of this particular course because it is meant to be a foundational course for you to understand. So in my opinion, I think just we covered as much as we could based on the amount of time that we have over the last 9 weeks. As you remember, we estimated the class to be covered from 8 to 10. So 9 weeks is enough, and just more is expected. As you expect more from your students as a participant of this particular training, I personally expect more to more from you to dig into the details of all the available resources that I have been sharing, and lots of resources are there. Just ensure that you don't get overwhelmed by the amount of resources that I shared you, or underutilize the resources that I shared you, because you have to balance, you have to strike balance between over just getting overloaded or underinformed. Okay, any other question? Arba Minch University coordinator, please give me your contact via our university Outlook address. So this is a question from Berhanu Molla. Berhanu Molla. Okay, any other question? Any other question? There are still people, I don't know, they are coming now, or maybe like just they joined and left because of network, but we have about under 45 people today. We are fine, as just okay. It is known that the nature of the data is main criteria to choose any method we are going to deploy. So while doing with unsupervised learning, how can we choose method for dimensionality reduction? For example, if the nature of my data is mixed, only categorical, then after we choose robust method for dimensionality reduction, the challenge part is choosing a number of n components for the final model, since sometimes either elbow, Pareto, script, plot end up wrong interpretation. So how to get the right one? Then how to evaluate performance? I suggest using, there is Salhoot approach. If we are talking about clustering, there are other approaches. I make it open for you to check. Salhoot is another approach in clustering, so you can combine. Yes, I observed the elbow technique may not work all the time, so you would have to use other techniques to decide the right clustering technique. So I suggest you research more about what kind of data you have. Since I don't know your data, I cannot definitely say this or that, but I suggest you digging deeper into the resources that I shared. If you don't get the right direction from the resources, I also suggest you to research more onto the data. And basically, the projects are meant to be educational for all of us, because I think most of the domain that you are exposed to, I don't know, but I only know the science of it. So from we evaluate the science of the machine learning application on your data, and depending upon the data, when you present it, the nature of the data, then just we will learn how it could be done. Yeah. Thank you for the question, though. Zanabu. Any other question? Any other question? Okay, Ermias Teklehaimanot, looks like you have you are having some, Ermias, it looks like you are having some network issue. Okay, I will be finishing this class and stopping the recording, and we can I will stay